Assalamu alaikum everyone. Dear student, in our previous lecture, we end up our last lecture in slide number 21. So these are some core concepts of linear algebra. So let us start with the column space or range of a transformation. So linear combination of column space is fundamentally the concept which we have to basically give the idea of range of a linear transformation of column space, the column space that spanned by column of matrix of a transformation, which basically generated when you take some transformation from Rn to Rn. So in that case, dear student, we just start with the column space of a transformation. Let us start with some concept like this. So column space of a transformation to find the basis for range of linear transformation or column space of a linear transformation t of x is equal to into x. So basically from here, if you don't know the transformation, so from these matrix you can see from where it is the domain and from what is the range of this transformation. If you can look over here, the student just look over here the matrix. The matrix is of order m cross n. So the transformation is from Rn to Rm. So the this is input is from Rn. So the input is multiplied with matrix A. That is, this is input which is from Rn. So it is consists of n cross 1 column vector. If you can multiply this with all, so you will ultimately get B. So the B is the range of T if and only if B is a linear combination of all these column vectors of A. So let us understand this with the help of one example. What does column space means? So uh, I means kernel of transformation. I always means to say we have to find out the solution of a homogeneous system, and column space of a I means to say which is equivalent to a range of transformation. I means I find all those elements of codomain which give me some B output AX equal to B, all those Y, that is give me some consistent solution for every B. So for that I call it as a column space of A, or sometime range of transformation T. So let us solve one example, dear student. If you can look over here, so this is a transformation from R5 to R4. The matrix of transformation is this one. So if you can look over here, if I can reduce this into a echelon or reduced echelon form, here you can see this is our this row column consists of pivot position. This column is again consists of pivot position. This column has no pivot, so this column is again consists of pivot position, and this column is against have no pivot position. So in that case, here you can see this column is correspond to this column in actual matrix, and this column which is correspond to second column of the actual matrix before transforming it into echelon form, and this column of row echelon form is equivalent to this first column of the actual matrix. So in that case, dear student, if you can look over here, the column space is consist of three vectors, that is this one, and then this one, or this one. And column space or range of a transformation is basically the subspace of codomain. So here you can see, dear student, we can take only four tuples, because in R4 we have four tuples or column which consists of four tuples. It means four order pair vector. Each vector is of four four element in every vector, because this is a the column space of range of a transformation is subset of R4. And in R4, dear student, the in R4, each and every element is consists of 1 cross 4 vectors or 4 cross 1 column vector. So if you can write it in column vector, then it can be written as 4 cross 1 column vectors. So if we can write in a row form, it is 1 class 4 row. So each and every element is consists of 4 element because of this R4. So I can say this is the basis for range of transformation or column space of this column space of this matrix A. So if you can reduce this the same matrix I'm taking just with one explained way. So if you can look over here, this is the basis for this reduce matrix, and this is column space of this what you call the this matrix A. In column matrix, this is C1, C2, and C4. So this I can just write it, this basis for range of transformation. So rank and nullity of linear transformation. Dear student, if you have a one transformation from vector space V to vector space W, the dimension of kernel of transformation T is called nullity of T, and it is denoted by nullity of T. Or this is dimension, I mean to say number of element in any any set. So if you have let us say one element in kernel of transformation, so the nullity will be 1. So if we have two elements, in that case the nullity will be 2. So in other way, in simple way, the number of free variable in the solution of Ax equal to 0 means to say uh, the free variable always correspond to nullity, and the number of pivot position uh, correspond to range of transformation or rank of a transformation, or one can say dimension of range of transformation is called rank of transformation. How many element in range of T? In previous example, if you can look over here, this is a pivot column. This is again pivot column. It consists of basically leading element in second row, and second element is 1. And this you can see the third row and third element is not 1. So the pivot shift to fourth position. So in that case this third position will be free variable. So dear student, if you can look over here, so we have fundamentally 1 and 2 pivot free variable. In that case, the kernel of transformation is consist of nullity consists of two. The dimension of kernel of transformation is 2, because it consists of two free variable, and the number of pivot are pivot row or either column, because dimension of row space and dimension of column space are equal. So in that case, the dimension of row means to say number of pivot rows 1, this is 2, and this is again 3, and number of pivot column, this is 1 pivot column, this is second pivot column, this is third pivot column. So dimension of row space is 3 and dimension of column space is also 3. So the dimension of range of T is equal to rank of transformation. If you can look over here, the rank of this matrix is uh, this is 3 because non-zero uh, row in reduced echelon or reduced echelon form is called rank of a transformation. In that case, this is non-zero row, this is again non-zero row, this is again non-zero row, and this is whole non-zero row. So in that case, the rank of this transformation is 3. So we go back. So, so the rank of transformation is number of non-zero rows in row echelon form or number of pivot in row echelon form of A. So as we have discussed in previous slide. So this is one of the very fundamental theorem and very important theorem that basically connect your dimension of kernel kernel space and dimension of range or dimension of what you call column space with the dimension of domain. I mean to say, if you have say n element in domain and the nullity of transformation and rank of transformation plus nullity of transformation equivalent to n. Or in case of rank of transformation is dimension of range plus nullity is dimension of kernel of transformation equal to dimension of domain. So let us take this. The here you can see the rank is number of non-zero element in of any matrix in a echelon or reduced echelon form. If you can see over here, this is reduced matrix. So non-zero rows is 2 and it has one free variable. So number of free variable correspond to nullity of transformation. So the nullity of this transformation is you can say 2 sorry 1 and the range of rank of this transformation is you can say 2. So the in that case rank of this number of non-zero rows in echelon or reduced echelon form of any matrix is this is number of non-zero rows, so it is 2, so the rank of A is 2. The rank of T is also 2. The nullity is the dimension of domain equal to number of row uh, number of sorry column because it is m cross n element m cross n element so it is a number of you can say we have to calculate the rank and nullity. So nullity is if you can go back in previous slide, the nullity is equivalent to if I can find out the nullity. So I have just put this term to uh, right hand side, and nullity will be equivalent to n minus rank of T. So in that case, nullity is equal to number of column of A minus rank of transformation. So in that case, here the n is basically the number of column in matrix A. So in that case, this is the uh, transformation from R3 to R3. So in that case, number of rows and number of column are equivalent. So 3 minus 2, the rank of transformation 2. So the nullity of transformation is 1. So let me correct this with this is just this one. So this is correct one. nullity of like t is equal to number of column, that is n, uh, or you can say number of column of A minus range of transformation, rank of transformation. So I just correct this. So dear student, if you can, let us take another example. So we have one transformation from R5 to R7. So to find the dimension of kernel of transformation, if the dimension of range is 2. So dimension of kernel of transformation is equivalent to n, where is n is the number of input or number of column of a matrix A minus dimension of range of transformation, like if you can go back into your slide this. So the dimension of kernel of transformation is equivalent to dimension of domain. Dimension of domain is what? Dimension of domain may be this dimension, number of linearly independent vectors over here. So dimension of kernel is equivalent to dimension of domain minus dimension of range. So in that case, if you can see in this example, so the dimension of range is 2. So n minus dimension of range. So the n is our, this is a transformation from Rn to Rm. So in that case, the n is 5. 5 minus 2, the range of transformation is, range of transformation or dimension of transformation is same. So it is 2. So the dimension of kernel of transformation is 3. So find the rank of T if the nullity is 4. That is, rank of transformation is n minus nullity of T. So 5 minus 4, because n is 5. So similarly, you have to solve this last part. So one-to-one and on-to linear transformation. What does it mean? One-to-one transformation, I means to say, if you put same images, the images are equivalent if the element in domain are equivalent. In that case, we can say these are one-to-one transformation. It means corresponding to every element in set V has some image in set W. In that case, we say T is one-to-one. But in here, in that case, if you can see two different element of domain has same element in codomain. So in that case, in order pair, the second element is repeated for this. This, let us say, second element, the image is 3, and the third element image is again 3. In that case, we can say these two elements have same image in codomain W. In that case, this is not one-to-one transformation. So let us take one example, and how the some transformation, linear transformation, is one-to-one if kernel of transformation is 0. I mean to say, if you have only one element in kernel of transformation, which is subspace of your domain L set, that is, if transformation is from Rn to Rm, so kernel of transformation is, dear student, always the subspace of Rn. It should not be the subspace of Rm, which is codomain. And if you can take kernel of transformation in any transformation is 0, uh, then in that case, dear student, the transformation is always one-to-one. If you can see linear transformation from M cross N matrix to N cross M, what kind of transformation it is? That transform M cross N element into N cross N element. It is, if you can put any element in this transformation and any matrix of M cross N, if you can take its transpose, that basically change its row into column and column into row. So this is the transformation is fundamentally the transpose of a matrix A. So this is always one to one because the kernel is consist of only m cross and zero matrix. Like if you have transformation, if you can elaborate this with the help of one very small example. If I take T is a transformation from 3 cross 2 matrices to 2 cross matrices, then the kernel of transformation is, dear student, uh, always the element like 3 cross 2, that is matrices of order which has 3 rows and 2 columns, that if you can multiply it with any transpose, then put it equal to 0. In that case, the kernel of transformation is always this like this one, and this is consist one of the element of this domain. So in that case, this is not just 6 element, this is only one element of this matrix. So in that case, this is a one-to-one transformation. So zero transformation is not one-to-one. You have to take it as a homework and do understand why it is not one-to-one transformation. So onto transformation, a linear transformation is onto if every element in W has some pre-image in V. So T is onto when W is equal to range of transformation. Let we These are some very fundamental results that will be very helpful while you solving some examples. Let T is a transformation from V to W be a linear transformation where W is a finite dimensional, then T is onto if and only if the rank of T is equivalent to dimension of W. That is, rank of T is dimension of W. So if it is one to one, if kernel of transformation 0 or nullity of T is 0. So let us that is another result that under what condition the any linear transformation is one to one and onto. That is, if you have any linear transformation which is both or both have same dimension, that is V is of dimension n and W is also dimension n. In that case, T is one to one if and only if it is onto. If it is onto, then it is imply this T is one to one. If it is one to one, then it implies T is onto when dimensions of domain and codomains are equal. So, dear student, let us sum up all these concepts with the help of example number 9. The linear transformation from Rn to Rm is given by T of x is equal to A into x. Find the nullity and rank of transformation and determine whether the T is one to one, on to, or either. Let us take first example. This is a matrix of transformation corresponding to Rn to Rn. In that case, the transformation, since the matrix is 3 by 3, so in that case, the transformation is look like from R3 to R3. So the domain element is, the dimension of domain is 3. The matrix, if you can look over here, the number of non-zero rows in this matrix is 3. The rank of this transformation is 3. And if you can look over here, the rank of transformation is 3. So in that case, if you can go back into the dimension sum of rank of transformation and nullity of transformation theorem, that says that rank of transformation plus nullity of transformation is equal to column of the M cross N uh, transformation. So in that case, dear student, the rank is already 3. So rank plus nullity equal to number of and the number of columns, sorry, the number of column is 3. So surely if rank is 3, then nullity is already 3. Because in that case, if you can go back into this theorem, that is rank of transformation plus nullity of transformation equivalent to n. So if rank is 3 and number of column is 3, then in that case surely the nullity must be 0. Otherwise the equality does not hold. So if you can see over here, this the in that case the nullity is 0. This is 1 to 1, and this is also onto, because the dimension of range and dimension of codomain is same. If you can go back, so I just apply this theorem. Both have same dimension. Then if t is 1 to 1, that if and only if t is onto. In that case, t is 1 to 1 as well as onto, because the dimension of domain and dimension of codomain is same. So in that case, the student, in second case, this if T is a transformation from Rn to Rm, in that case n is basically 2 and m is 3. So the matrix of transformation is 3 rows and 2 columns. So in that case, the transformation is from R2 to R3. The dimension of domain is 2. The rank of T is the number of non-zero rows in echelon or reduced echelon form of this matrix is 2, 1, 2. The rank of T is 2. So nullity of this transformation is again 0, because the if you can see over here, so the this is 3 cross 2. So the range, sum of rank plus nullity must be equivalent to 2. So this is only possible if nullity is 0. So this is 1 to 1 transformation, because the nullity is consist of 0. Kernel of transformation, I mean to say the kernel or nullity, it is more or less same. So the kernel of, whenever kernel of transformation is 0, and we take one theorem like here, the if you can look over here, that is the transformation is 1 to 1 if and only if kernel contain only 0 vector. In that case, dear student, if you can go into the examples, or example number 9. So here you have the kernel of transformation is 0. I mean to say nullity of this transformation corresponding to this matrix B is 0. It is 1 to 1. So another thing, that it is not onto. So you have to see other C and D transformation and solve this in your home, and do consult these examples, and we will discuss why these dimensions are like this one. So take it as a homework. So isomorphism of a vector space, two vector spaces of same dimensions are isomorphic if they share some characteristics, uh, if they have same dimension, if they have basically same number of elements. In that case, we can say these are uh, basically isomorphic to each other. Like such as the four-dimensional vector space. These are all isomorphic to each other. Basically, the R4 spaces consists of fundamental vectors are 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So M41, it means to say it is all space of 4 cross 1 matrices. It has 4 rows and 1 column. So it is against again equivalent to some A 0, 0, 0, 0, then another vector 0B 0, 0, 0, then 0, 0, C 0, then 0, 0, 0, D. Then 2 by 2 matrices, space of 2 by 2 matrices. As in lecture of my dimension and basis lecture, we have take 2 by 2 matrices consist of 4 basis matrices that span the whole 2 by 2 matrix space of 2 by 2 matrices, which are 1 0 0 0, then 0 1 0 0, then 0 0 1 0, then 0 0 0 1. These are four and this is again consists of uh, four bases in this P3, and this is again four-dimensional vector subspace of five-dimensional space, which is consists of four elements. So these are all isomorphic because the dimensions are same. In that case, it has four elements. In that case, it has also basic basis, four-dimensional basis, and this is again four standard matrices that span this basically span this whole 2 by 2 matrices, and this is again 4 cross 1 column matrix. This is again, it has again four fundamentally four you can say uh, you can see it has again four vectors of 4 cross 1. So these are all isomorphic. So dear student, these are all about our lectures of this week. Dear student, stay at home, and thank you all for attending this lecture, because today lecture I just divide it into two lectures because these are quite important, and please I will share some examples with you, and in I hope in next lecture I will discuss its examples, more examples of this topic, and these are quite important topic. So please stay at home, and please save yourself as well as your family. Allah Hafiz.